Hello everyone, my name is Yohan. I'm from third year BTech Robotics and AI. So my research topic is that personalized driving styles in autonomous vehicles. So why do we need personalized driving styles is that every person has their own desire of driving style depending upon their age and personality, etc. As there is no one size fits for all solution, we might be needing a different driving style for everyone, for every person who owns an autonomous vehicle. Currently, there are autonomous vehicles with just a generic type of driving, and there is no personalized driving in autonomous vehicles. So that gives us a gap in this technology to further research upon. So the first paper which I have taken for literature review is titled "Learning Driving Skills for Autonomous Vehicles from Demonstrations," which has been published in the year 2015. So the main objective this paper tries to achieve is to get the longitudinal control of the car similar to the driving style of the user. So instead of manually tuning the parameters of the controller, they are going for an inverse reinforcement learning based approach to get the same cost function with the data which has been collected during the driving of the car. So the methodology that they have used is that the car has sensors equipped in it, and using the sensors while the person drives the car, they get the data and represent the data as trajectories. And those trajectories are represented in the form of 2D quintic splines. And using those trajectories, they try to get the cost function using the inverse reinforcement learning technique. And by doing this, they are able to achieve longitudinal control in highways. But the limitation comes here such that the 2D quintic splines are represented as a linear combination, while the real world scenario might not be a linear entity. It could be a non-linear, and because of that, the complete user's driving style could not be captured. So that comes as a limitation. And also, this is only tested on highways. So on urban environments, when there is traffic and so on, it could not be used. So the second paper which we have taken for a literature review is titled "Aggressive Driving Behavior Scale: Developing a Self-Report Measure of Unsafe Driving Practices." So this has been published in the year 2003. So this is not related to mimicking the driver's driving style, but this paper gives us a thorough understanding of why the person or why the driver takes a particular action while driving and what is the intention behind it. So basically, they have created a scale, a self-item, a self-report tool using college students. So the participants are around 200 undergraduate students with driving experience, and they have using principal component analysis. They have differentiated or grouped the participants into two categories. One is conflict behavior, which comes under honking and rude gestures, etc., and the other is speeding. So they have also validated the grouping based on their questions directly related to their personality. But there comes the limitation, as it is a self-reported scale. There could be some bias, or there could be noise in the metrics, as some people may not be able to or might not accept their bad behaviors. So that leads to the noisy index making. So the third paper which I have used for our literature review is titled "Modeling and Characterization of Driving Styles for Adaptive Cruise Control in Personalized Autonomous Vehicles." This paper has been published in 2017, where they are trying to quantify the individual driving styles or individual users' driving style and integrate it directly to the adaptive cruise control of the system or car to mimic the user's driving style in a longitudinal path. So the methodology that they have used is that they collect data such as time headway, inverse time to collision, acceleration deceleration patterns from the user, and using those values they train a non-linear car follow-it model to get the model to give output to the adaptive cruise control of the car. And the adaptive cruise control changes its control gains depending on the output from the car following models they have used, and based on that the car controller gives the command to the motors to run accordingly. So the main limitation comes here is that as it uses adaptive cruise control for controlling, it could be only used for longitudinal control, and lateral control or maneuvers in urban environments could not be possible. So the fourth paper which I've used for a literature review is titled Human-like Driving, Empirical Decision-Making Systems for Autonomous Vehicles. This has been published in the year 2017. So this paper doesn't focus on mimicking or personalization of users' driving style, but what it does is that makes the car to drive more human-like, not the user style, but more of a human-like, so that it could be different from the generic driving style which other self-driving car uses as of now. So they have used depth sensors, and they use a deep learning network to make decisions that blend in with human drivers on a real road. So the methodology they have used is that they have used LiDAR for depth sensors to capture the 3D environment, and they have only used partially RGB data. They are also training a 6-layer deep neural network to get the commands such as it could be similar to the human driver's decisions. The main limitation comes here is that they are heavily dependent on depth data and only partially used RGB data. So that could make the car to lose some important information about the environment. And also it doesn't personalize the driving style, it only makes the car to drive more of human-like. So the fifth paper which we have taken for a literature review is titled Driving Preference Metric Aware Control for Self-Driving Vehicles. This has been published in the year 2019. What they're trying to achieve is that mainly longitudinal control of acceleration and jerk values depending upon their user's preference. So to develop a driver preference metric which could accommodate the acceleration and jerk values of the preferred values of the driver, and using that they are controlling the vehicle on a longitudinal path with some little maneuvers towards curvy roads or so. So the methodology is that they have defined the driver preference metric using the data collected from the driving of the user. The data mainly consists of acceleration and jerks, and using those values as the minimum and maximum values, by setting a limit they represented the same as GG diagrams, and they have used a speed planning algorithm to follow those GG diagram and give the necessary speed to the motors accordingly when going through curvy roads or straight line roads. The main limitation comes here is that they only focused on acceleration and jerks. They have not considered distance other vehicles and lane changing parameters, etc. So the sixth paper which I have used for our literature review, and it's also a base paper, which is titled Maverick, a data-driven approach to personalized autonomous driving. It has been published in the year 2023. So Maverick is trying to achieve a personalized autonomous vehicle system using a data-driven approach to match the user's driving preferences. This approach does not only mimic the user's driving style, but also tries to understand the intention behind the action of the user and implement the same while driving autonomously. Hence, it doesn't only mimic the user's driving style, but it also creates a thinking twin of the user, so that the model will be able to think like the user and take decisions on the environment while driving. So the methodology is that they collected the driving style of the users through a simulator, and they have trained the neural network to uh, predict the high level parameters of a low level controller, such as following distance, lane changes, velocity predictors, etc. And they have also included an aggression dimension which has been derived from the aggressive driving behavior scale from our literature paper 2, and using that aggression dimension they are able to predict the intention of the action and also mimic the driver's driving style. And the major limitation comes here is that the aggression measured by the noisy self-report scale is from paper 2, and that could be overcome by searching for other similar solutions without reliance on the self-report scale. So we come to the comparison section of this video. And the first paper, which is our base paper, uh, gives has a model that could take in images, maps, and aggression index such as inputs. So it is a multi-model system. And the intention modeling, yes, it is intention modeling. It could be used to predict the intention behind the action. The planning method is goal condition trajectory, and it could be used in real world autonomous driving systems. And for the second paper, learning driving styles for autonomous vehicles in demonstration, it uses lidar plus cost features, and it is not multimodal. It just uses two inputs, and it won't be able to predict the intention behind the action. And it's also a cost-based imitation, unlike the goal condition trajectory from Maverick, and it only mimics the human's driving style. And the third paper is driving preference metric aware control for self-driving vehicles. It has low dimensional trajectories, which is linear trajectories, which couldn't capture the complete nature of the driving style. So there is also no intention modeling, and it is also preference based, unlike much superior goal condition trajectory. Use cases, it only predicts the styles, and it could only be used for a longitudinal control. And for the fourth paper, which is modeling and characterization of driving styles for adaptive cruise control in personalized autonomous systems. Input modalities, it is simulator visuals. It is only single input system. Intention modeling, it has no intention modeling. And planning method, it is a supervised imitation. It is only used in simulated imitations. And the aggressive driving behavior scale is a self-reported measure, and it doesn't have any kind of imitation or personalization behaviors. It is only behavior profile. Human-like driving empirical decision-making system for autonomous vehicles. It doesn't have any mimicking or personalization of driving user. It just makes the system to drive like a human, and it could not be possibly related towards personalization. So why did we choose Maverick as our base paper? So there are three main reasons. The first one is it is rich multimodal fusion. It was able to effectively combine different kinds of data from the sensors, and also driver-centric data such as aggression indexes. And because of its rich multimodal fusion, it is able to model the intention behind the actions of the driver. So while doing that, the car is able to take important decisions as similar to as how the driver would have taken in that particular situation. And there's also goal condition planning instead of just behavior cloning or preference-based ranking methods given in other research papers which we have seen. And the conclusion is that Maverick is the best paper among the literature reviews which we have conducted, uh, since it is not only mimicking the driving style of the user, but also it was able to mimic the thinking capabilities and take appropriate decision when needed. So the main limitations with Maverick is that it majorly depends on aggressive driving behavior scale, which is a self-reported measure. And since it is self-reported, it could contain bias and noise in it. And also the person's mood varies from time to time. So while driving the car, he might be in different mood. So the self-reported aggressive driving behavior scale could not be applicable while the person drives the car, or is in traffic, or in other situations. And also one single numerical index couldn't effectively capture or explain for all kinds of possible situations while driving. So I propose a solution where we could eliminate the aggressive driving behavior scale, and we could replace that scale with a data-driven aggression index, which we could collect during the driving of the car. So this is the existing architecture which they are using in this paper, where there are following distance predictor, lane change predictor, velocity predictor, and style predictor all in parallel, and they are using an LSTM network to predict the high level parameters. Along, along with the input data from the sensors, they are adding the aggression driving index, behavior driving scale. So that value we could replace with our own aggression index, so that the noise will be eliminated in that self-reported value. So our proposed solution's objective is to replace this noisy self-reported aggressive driving behavior scale with the more robust data-driven aggression index using multimodal sensor fusion. So what we'll do is we'll remove the ADBS and we'll incorporate an inverse reinforcement learning technique to gather the data from the sensors and from the driving data, and using that reinforcement learning we'll be able to derive the cost weights which we could use in place of the ADBS value. So basically we will be collecting two kinds of data. The first one being physiological data, which is heart rate variability, the root mean square of successive differences will take, and the galvanic skin response along with eye tracking or the pupil dilation rate. The behavioral data is already been taken in this paper, and using the data they have constructed the architecture. So instead of the ADBS, we will be taking physiological data while the user drives the car, and these three data could be used to infer the cost function of the inverse reinforcement learning technique model. So the measured behavioral and physiological features can be converted into the corresponding parameters as you can see here. So the first one being aggression score, which is which is dependent upon the acceleration values of longitudinal and latitude, and also the comfort violation where the jerk value is given a threshold of 2.5 meter per second cube. And on the physiological feature side, the stress index is a cross product of heart rate variability and galvanic skin response. And on the cognitive load, it is a derivative of pupil diameter. So this is the proposed flowchart for this model. So we'll start collecting the data, which is behavioral data and physiological data, and we'll pre-process it and give it to the feature engineering. And from there it splits to two components. The one EM clustering for cautious, normal and aggressive is already been done in this paper, so we need not touch that. We are just going to now take the trajectory features, which is acceleration, jerk and time to collision, and by using that we'll infer the cost weights by using inverse reinforcement learning. And after inferring the cost weights, we'll give it to the multimodal fusion part, where the cautious, normal and aggressive data and our own inferred weights will be fused, and that could be used as a aggression index instead of the aggressive driving behavior scale. And by doing that, we'll be able to give the neural network our own aggression index to predict the high level parameters for a low level controller, so which would output the personalized driving behavior. So on the conclusion, uh, this model will be able to learn what driver truly values based on their actions rather than a self-reported measure. So it infers the driving parameters and the intentions live while the driver drives the car, instead of relying on self-reported measure. So while combining self-reported measure, it could lead to some bias or noise in the model. So instead of that, we'll be combining the physiological response along with the behavioral response. So it will be able to compare and cross-validate between both the parameters on the spot in live. So hence reducing the noise in any single measure. So these are the references I have used. Thank you.